Hello everyone, welcome to Chapter 12, Linear Regression and Correlation. We will begin with linear regression first. It's nice to begin here because it's more to do with math. So you are familiar with this, and so it will help us, get started and see how it's mathematically relevant in a statistical problem. Okay. So we use this in many applications, linear regression. It is used in business, finance, in sciences. But in terms of statistical calculations, we see that in almost all quantitative data analysis, linear regression is utilized in some form or the other. Yeah. Now let's begin to describe this. So we have linear. Okay, let's consider the word linear. What's the word contained in linear? Isn't it the word line? So we are trying to use linear regression for two variables based on a linear equation with one variable. Okay, what does it mean? Well, a line, if you look at a line, we usually graph a line using two variables, right? Say the line is like that. Then you write the line as, say, y equals 5x plus 3, something like that, right? So we write an equation of a line, a linear equation, right, with two variables, x and y, isn't it? So we are trying to do the same thing here. We're going to use this idea of line to see how two variables are related and how we could write one in terms of the other. Okay? So linear regression, I'll just write what I said earlier. Linear regression for two variables is based on a linear equation with one independent variable. This sentence or statement might seem complicated, but it's something that we do very intuitively. In fact, when we wrote this, y equals 5x plus 3, we wrote the y, which is the linear equation, in terms of one independent variable, which is x. So we can actually say that your x is your independent variable, and the y value will depend on this x value. Whatever you give x to be the value, that will give us a corresponding output for y. Therefore, y becomes the dependent variable. So typically, we choose a value for x. We substitute that value in the equation. And for instance, let's say x is 2. Then 5 times 2 is 10. 10 plus 3, 13. So y would be 13, which is a value that depends on the x value 2. When x is 2, y is 13. So we're able to solve for the dependent variable by providing or supplying an independent variable. Okay. There's another name for the independent variable. It's known as the exploratory. In fact, it's got two more names. Okay. It just depends on the context. Okay. If it is economics, then they like to use the word exploratory instead of the independent and so on. So it's known as the exploratory variable or the predictor variable. It's important to know these other names because actually when it comes to research, when you are working on a thesis, then we use the words predictor more frequently than the word independent. Well, these days, it's not a big deal, but it's more of the language in academics sometimes. Also, it is nicer to use certain words because predictor helps you to predict, right? So this is a variable that helps you to predict the dependent variables here. There's a reason why they have these names. And the y, the dependent variable, is also known as the response variable because it responds to the value that was given for the independent variable, right? And how do we know which one is dependent and which one is independent? Well, you should always ask the question, does x depend on y or does y depend on x? Initially, we won't know which one is x and which one is y. So you have to identify the two variables and ask which one depends on the other. We've discussed this before, but it's a good idea to recall it. Say you are trying to measure the growth of the plant, the height of the plant, okay, say in inches, versus the sunlight, the amount of sunlight. So the growth of the plant in inches versus the amount of sunlight, the number of hours of sunlight. So then I talk about hours of sunlight. And then height of the plant. You have, these are the two variables. These two can vary, right? The hours can vary, the height can vary. So these are two variables. So now ask yourself, do the hours of sunlight depend on the height of the plant, or does the height of the plant depend on the hours of sunlight? When you think about this question, your answer becomes very clear, okay? So you know that the height actually depends on the sunlight. Right? No matter what the height of the plant is, the sun continues to shine. So the sunlight is independent, the hours of sunlight is independent of the height. So then you know, based on that question, you will assign the height to be y and the sunlight, the hours of sunlight, to be x. This is crucial because then you know which one goes on the x-axis and which one goes on the y-axis. So the x-axis will be the hours and the y-axis will be the height in inches or centimeters, right? However we measure it. And therefore, when I draw the line, it makes sense because my height will now be the y and my hours will now be the x. So if I plug in x as, say, 3 hours, I'll get a corresponding y as the height. Now, instead of hours of sunlight, say it was days of sunlight, then days would go on the x. And then if I say add, x is 3, that would mean the third day and what the corresponding height would be, right? So if I were to draw this line like this, then you can actually make a lot of inferences, right? So you can see what time and what for and its corresponding height for a particular value for x. So that's the reason why we really need to know which one is dependent, which one is independent. Okay. Then we also, if you recall again from your algebra, we have the y-intercept. As the name says, y-intercept. Intercept means something that crosses, right? So what is that something? That something is this line. The whole deal here is about the line. The point where the line crosses your y-axis is called the y-intercept. Your line, the linear equation, right? So let's say this is the point where the line crosses the y-axis. Then we have something called the slope. Remember the slope? Yeah, rise over run. A slope basically in English means the slantness, right? Slantness or the steepness of a line. So this describes slantness or steepness of a line. And if you recall, the equation of a line, we've seen many equations. We've seen the standard equation of a line, right? Quick algebra lesson here for us. We've seen y equals, let's start with the standard one. The standard one would have been ax plus by equals c. This is the standard equation of a line. Then we saw y equals mx plus b. This was the intercept, the slope-intercept form. Then we also saw y minus y1 equals m times x minus x1. This was the point-slope form. Out of the three forms, we will be utilizing the slope-intercept form here. And if you recall, this M is your slope and this B is your y-intercept. That's why we describe the y-intercept and the slope. Okay. So the whole idea of this equation written in slope-intercept form is because of some things that you can readily see without having to calculate, right? In your equation, y equals mx plus b, you can readily see your slope and your y-intercept, okay? So let me give you an example here. Let's say y equals 8x minus 11. So you can readily see that your slope m is 8 and your b, which is the y-intercept, is negative 11. You didn't have to calculate. That means, based on your algebra knowledge, you know that the slope here is positive, right? So positive slope means your line is increasing. So you know that it's going to be slanted and increasing, not necessarily slanted that way. It could even be slanted like this, right? It could be like this. But you know it is increasing, so it's not going to look like this, right? That's not going to happen. So you know the increasing part here. And the y-intercept tells us that the graph crosses, this line crosses y-axis at 0, negative 11, right? That's the coordinate on the y-axis. It's always 0, the y value. So it's going to cross 0, negative 11 and go up. So you could actually quickly begin to sketch. So it gives us a lot of details here. Well, if my question was not that, instead if I said evaluate when x is 4, evaluate this equation when x is 4. Evaluate. If you look at the word evaluate, what's the word contained in it? Value, right? So it means you have to find the value. In this case, our value would be the y value. So y equals 8 times 4 minus 11. 32 minus 11 would be 21. So when x is 4, you evaluated y to be 21. So we've seen these in algebra before, so hold on to this and we'll quickly look at our first question. Okay, so Jerry is a refrigeration technician and he owns, okay, see an error there, air-conditioned repair business. Anytime he makes a house call, he charges $65 plus $40 per hour of work. A linear equation that expresses the total amount of money Jerry earns per visit is given to be y equals 65 plus 40x. What are the independent and dependent variables? What are the y-intercept and the slope? Oh, very nice. Well, come back here. In fact, they did some work for us already. Technically, we should be even coming up with this equation. Well, they gave us the equation, so that's good enough. But if you go back to the question, you can see that he charges $65 plus $40 per hour of work. So if he goes, perhaps it's just inspection charges, right? The fact that he visited that house, he's going to charge them $65 even if he didn't do any work. The fact that, meaning if he didn't do any repair work, the fact that he visited and inspected the place would be $65. So that's flat rate. Plus $40 for every hour of work. So if it's 1 hour, it's $40 plus the 65. If he works for 2 hours, it's $40 times 2, right, for 2 hours, which is $80 plus 65. If he works 3 hours, then it's $40 times 3, $120 plus 65, and so on. Does that make sense? So that is what is given to us as y equals 65 plus 40x. We need to understand what this x and y represent. So for that, go back and see what each one of them would actually give us. Okay. Now it says the linear equation that expresses the total amount of total amount of money that Jerry earns per visit is given to be this. Okay. So this whole equation, which is basically represented by y, this gives you the total amount of money that Jerry makes in a house call. Okay. So how is this money calculated? 65 is the flat rate. 40 times x. So we know, we kind of mentally ran this through, right? 40 times x. So x, what does x represent then? X should be the number of hours or the amount of time that he spends in that house, right? So if he spends 1 hour, then it's 40 per hour of work. So if it is 2 hours, it's 40 times 2 hours of work. If it's 3 hours of work, it's 40 times 3 hours of work. So you can clearly see that the x actually represents the number of hours of work. So if you establish what each of them stand for, then you get your x and your y, right? So then you can see, well, does the total money depend on the hours or does the hours depend on the total money? Think about this, right? Which one is independent? Definitely the time that Jerry works, right? The repair time, that is what is really independent, because the amount of money he earns based on that is what will result in the y. So y actually depends on x. That's the way it is set up. It's always set up as y is always a dependent variable and x is always the independent variable. We can see that, but we are able to go back and see what they actually represented. So y, the total money, depends on how many hours he works. So x would be the number of hours worked. So this would become our independent variable. And the total amount of money, the y, is our dependent variable. So we answer that part. What are the y-intercept and the slope? This is a very mathematical question. So let's write that out here. 65 plus 40x. Now please remember that you always have to put it in the y equals mx plus b format. Right now it's in the form y equals b plus mx. So you really want to make sure that your x term comes first. So please rewrite the equation as 40x plus 65. All right. So don't just go by the first term you see, go by the template, the format. So now that it's in the format that we are familiar with, this, well, let me also write y equals mx plus b. That way I can kind of box this to show you that your slope is 40. And then I can box this to show you. That's a very light color. I can show you here that the y-intercept, b, is 65, positive 65. So the slope is 40 and the y-intercept is 65. If the question wants you to write it as a coordinate, please make sure your 65 is written as 0, 65. Drop. All right. So now for us to see how our points, how our data values are displayed on a chart, we use the idea of Scatterplot. And we discussed this early in the course too. So Scatterplot is an easy way to display the relationship between two numerical variables, right? If it's not numerical, if it's qualitative, we can't really plot them, because how would you get their coordinates? So this is a way for us to display the relationship between x and y. And when you are able to display a graphical view of x and y, then this is what we will use to lead our discussion into linear regression and correlation, the very topics of this chapter. Okay, so then let's take a look at a data set. A county commissioner wants to paint a very important bridge in the community. The community engineer gave him the cost estimates based on the length of the portion the commissioner wants to paint. Create a scatter plot for this data. So we have two columns, the length of the bridge and the cost of painting. So the length of the bridge is given to be 100, 200, 300, 400, and the corresponding cost of turn is given to be that. Okay. Well, we don't know what the measurement could be, so I'm going to call this feet. Okay. And the cost of painting is already given to be in dollars, so I'll mark this as feet. Okay. To paint 100 feet of the bridge, it costs 20,000. To paint 200 feet of the bridge, it costs 40,000, and so that's how you understand this. Now you can do this manually, okay? Meaning you'll have to decide which one is X, which one is Y, and use that information to get your X and Y columns, right? We could then once we have the X and the Y assigned, then you could draw your chart, right, on the graph. Then you can get the X and the Y, and you'll know what ones to mark as X and what to mark as Y. So if you recall, we said, well, to know which one is dependent and which one is independent, we always know that your X is independent and your Y is always dependent on that. It depends. Y depends on X. Okay. So ask the question. Does the length of the bridge depend on the cost of painting, or does the cost of painting depend on the length of the bridge? Both are variables. These are the two variables we have. So you can begin to see that, well, the length of the bridge is not going to change, but the cost of painting is affected by the length of the bridge, isn't it? So if you want 100 feet length of bridge, then it costs you 20,000. So the length depends. The length defines what the cost will be, right? The length defines the cost. Therefore, the cost actually depends on the length. So reasoning out like that, we can see that the length of the bridge must definitely be our independent variable. That. And the cost of the painting should be your dependent variable, which is Y. Okay. So now that we've identified X and Y, you can go here and to your graph and do 100, 200, 300, right? And then go over here, and then if you had them all in terms of say you jumped by 10,000, so this would be 10,000, 20,000, 30,000, and so on. Yeah, and then you could begin to plot. For instance, the first one you'll plot will be 100. This is X, right? This is Y. So this would be basically 100, 20,000. So 100, 20,000. The first point will be like this. So you're going to get all the 4 points for this using the scatterplot idea. Now you could do it graphically, manually like this, or you could do it as a graph using Excel spreadsheet. Okay, remember we have the Excel as it's a free tool for you as a student. So go ahead and use Excel, or you could use your graphing calculator. Okay, so if you're using a graphing calculator, you'll have to go into your, I'm talking about TI-84, okay? This is TI-84 plus. So therein, you'll have to go into your, go into Stat button, click on Stat button, and then it says, it says Edit Calc Tests, and then under Edit, you have Edit, Sort A, Sort D, and so on. So stay on Edit, go down to the first one, number 1, Edit, Edit, Edit. Okay, so go to L1 and enter this data in L1. Okay, the length of the bridge. Okay, this one goes in L1. So type 100, punch in 100 and hit enter. That takes you to the next row. Then type 200 and hit enter, and so on, right? And then enter this information in L2. Once you're done with these, okay, you want to go to the STAT-Plot. STAT-Plot, you can access STAT-Plot by clicking the second button, the blue button, and the STAT-Plot button, which is Y equals button. Okay, so use that and go to plot 1 and make sure that the plot 1 is on. If it's off, move it to the on. And for the type, go to the first type. The first type is your Scatterplot. Okay, you have 6 icons there, images of graphs. So go for the first one. Then it says Xlist. So go for L1. Ylist, go for L2 because you have identified L1 as the X, right? The X and the L1 are matched and the Y and the L2 are matched. So make sure that your Ylist is L2. Then go down to mark. Mark shows you how to mark them. Do you want it as a square, as a plus, or as a dot? Square is the preferred choice because it's just visible. And you have only 4 points, so it's not really bad. So if it is Excel, then it's different. You can use the dot or colored dot and things like that. If it's calculator, we just use this. And that's it. And then go to make sure there is nothing in your y equals, okay? Because then it'll get confused with that information. So go to y equals and make sure that you clear everything. Any equation that was typed there before, make sure you clear that. All right, then go to zoom and click on the zoom button, right? That's the gray button on the very top. And go down to number 9, which is zoom stat. And then hit zoom stat, and that gives you the scatter plot. Good. Now, if you did the scatter plot on the Excel sheet, you will do the same thing. You'll plug in, you'll build 2 columns, one for the X and one for the Y, and use the the scatter plot button there from your charts. You should look at a graph that looks like this. You should get a graph that looks like this. Yeah. And if it's too far out for you, you can always zoom in to see it closer. And further details are made available in your assignment. So if you want to track it there, you're very welcome to do that. All right, so that gives you, and then of course go back and fix the window to scale your size. If you can't see some dots, you don't see all the plots or you don't see any of the plots, it could be because your window, the scaling window was very off. So go back there and fit your scale. All right. So this kind of tells you how the dots are lined up. Okay. Now our whole focus here is to see, are they closely lined up as a line? They're not going to be perfectly aligned, right? That's not that this is a real life thing. So they're not going to line up perfectly to form a straight line. But do they more or less form a straight line? Yes, it seems like they will. Most of the points will pass through a line, or at least they all can follow a straight line with less deviation. So we got that. We'll look at another example. This is a similar one. So it's in fact kind of an extension. We're giving you some extra points, right? So in the previous table, I had only 100, 200, 300, and 400. Now we have given you extra points, extra coordinates. So go ahead and if you want, you could clear your lists. And if you want to clear, you could use L3 and L4 if they are free. But if you want to use L1 and L2, what you will do is you'll have to clear the current list. So go to Start button, and then you go to the Edit. That's where we did the edit, right? To enter the values. Now, instead of clicking on number 1, Edit, go down to number 4, Clear List, CLR List, Clear List. So go to Clear List and clear, and then it will say which one you want to clear. So go ahead and clear L1. Now, in my TI-84 plus button, calculator, the L1 button is behind the number 1 button, right? So I'll have to do 2nd and 1 in order to access L1. So what I will do is I'll have to go to 4, clear list, and then I will punch in 2nd L1 to clear list 1. To clear list 2, I'll have to do that again. I have to go to Stat, Edit, Clear List, that's number 4, and then do 2nd L2. That way my L1 and L2 are free, everything is cleared up again to punch in the values. We already established that this has to be X, so this will be your X, which is your L1 in this case. This will be your Y, which will be L2. Again, if you're using L3 and L4, make sure you are calling upon L3 and L4 when you do the stat plot, right? Remember, when you go to stat plot, there it will say Xlist. Stat plot, you know how we access stat plot, right? You go to 2nd Y equals button. So you go to plot 1, and if it's on, make sure if you just used it, it will be on. Go to the same type, select the first type, which is the scatter plot. Then Xlist, make sure there, if you're using L3 and L4, write it as, type in there as L3, or use the second, third button, and Ylist will be L4, second, fourth button. If you're using L2, L1 and L2, then you make a corresponding change. All right, go ahead and hit, choose mark and then hit enter, and then go to zoom and number 9, which is your zoom start, and see if your graph looks like this. You can pause and play with it a little bit to see if it matches with this. Okay, this is how it should look. Okay. So this is just drawing the scatter plot. We are creating the scatter plot. Okay. This is what we will use in order to do a little more on correlation coefficient and correlation and linear regression. So let's talk about least squares criteria for best fit. I want to bring in a few pointers. First of all, your data rarely fits in an exact straight line, okay? So do not expect the points to line up in an exact straight line. Because it's not going to be that way, we must be satisfied with rough predictions. In order to make rough predictions, we have to see if we have a set of data whose scatter plot appears to fit a straight line. So we should just ask that question, does the scatter plot appear to fit a straight line? If the answer is yes, then it's good, because then you can use information about that line, use the equation of a line, and then go on further from there. And if that's the case, we call it the line of best fit. That's also known as least squares. We'll talk about that shortly. Okay. The line, if you're able to fit the scatter plot close to a straight line, that line is called the line of best fit. And that equation of that line, okay, equation means y equals mx plus b format, right? So you can see the line, but you need to give it an equation. So the equation of this line is called the linear regression equation. Okay. So here, if I were to say, want to draw a line through these points, okay? Notice that I was able to make this line pass through these 3 points. Okay. I could have also drawn other lines, right, to cover more points maybe. So I could have another one like this. It's not the best line, I would think, because it only passes through 2 points. Okay. Then I could use another one. Is this a good line? Actually, it's a bad line because it's not even running close to the other points, right? My line, all the data points must be close to this particular line. So I don't see that. Then I probably can try. Let me see if I can get these 3. Somewhat okay. But you notice that the purple line is deviating way, because there are 3 points that are deviating way away from the purple line. So you can see that we can draw as many lines as we want to make as many points appear on it, or at least get close to it. But among these lines, we need to find the line of the best fit, isn't it? So for that, we want to, just intuitively, we understand that we're looking for a line where we try to get most points on it, but if the points are not lying on it, we want them to be not too far away from it, right? The distance of the points that are not on the line must be minimum, right? For the distance between the point and the line. You want that distance to be minimum. For instance, this distance here is really huge, right? That point is too far away from the pink line. But then if you look at this pink line here, this point is so close to the pink. This one is not lying on it, but it's close to the pink. And this distance from the pink, yeah? So we are really trying to see how these are, how we can bring them really close. Now, if you look at the green one, okay, let me remove those ones. If you look at the green one, look at the points that are away from green, okay? So this one is good. This one is away from green. See how far away this is from green? This. If I stretch this some more, I would have that. So green is really having too many points that are away from it. So green is clearly not the line of best fit. The purple also doesn't look like that. The pink one seems to do the job much better. But we can't be subjective, right? You can't just see, eyeball it, and you can in some cases, but sometimes if you, this was just what, 1, 2, 3, 4, 5, 6, 7 points. But if you had 700 points, how would you even determine that? Therefore, we approach it through math, because math is very structured. It includes all these things. And there are calculations that you can do so that all the points are taken into account, and the distance between the point that's away from the line and the line itself, the corresponding point on the line, would be measured. Okay. So if you can see, let's just use this green example here. Okay. This point here is the point on the green line, but this is the point that is away from the green line. So this is the original point, and this is the predicted point. Right? So we want this distance between the predicted point and the actual point, to be small as possible, because that is an error, right? The fact that the original point is not on the line is an error. So we want to minimize that error. Okay. For that, we actually consider something called sum of the squared errors, okay, SSE. So take a look at this data set. Here we have this data point, okay, this is a point of interest now. So this data point is x0, y0. And what you have is, we're saying, well, this blue point, I'm sorry, not the yellow point. The blue point is the data point. The yellow point is the point on the line, okay? And in statistics, when you have this hat-like symbol, right? Remember, we even used p hat for sample proportion. When you see the hat, you know that means it is predicted. It's not the actual value, it's the predicted value, okay? So sample proportion is not the actual population proportion value, it is close to it, right? All right, so we're talking about the distance between y0 and y0 hat must be minimized. That's what it means. So sometimes the point appears above the line, sometimes the point appears below the line. So if you took the distance, then sometimes you'll get a positive distance, sometimes you get a negative distance. But we want the distance, therefore it can't be positive and negative at times. We want it to be always positive. So that is the reason why we take the absolute value, okay? And we also square it, and so it's called the sum of the squared errors. So if I can predict the points, and if I can draw this blue line, right, I should be able to give an equation for this blue line, right? In general, this will be y equals mx plus b, but this blue line can be, it's a painstaking process, the calculation, if you were to do it by hand, because you're going to consider all possibilities of these of these lines and choose the one that is the best fit. We have the calculator, thankfully, and software these days to help us do it. So y equals mx plus b. On the calculator, though, it appears as y equals ax plus b, the regression equation. Okay, y equals ax plus b. So it's not using m and b, it's going to just use a and b. Doesn't matter because your a is now your m. Okay, so we're going to do an upcoming example using the calculator to find out the linear regression line and equation. Okay? A professor furnished this data showing the number of questions correct out of 20 that 10 of his students have taken in a test designated as X values. Y values are each individual student's inclination by percentage to taking test. How much they are inclined, right? What percent they are inclined. They're 94% inclined. They are just 5% inclined. 70% inclined. So you understand that. Using a calculator or statistical software, find the linear regression line for a student attitude given a value for the score for X. Okay. So let's come back and try to first identify which one is X and which is Y. The numbers that were accurate and the inclination are the two columns. You have to decide which is X and which is Y. In fact, they helped us with that too, right? They said the number of questions correct out of 20. So you can clearly see that these are values within 20. So it must be your X values. These are the test scores, right, that they got correct. So this is the X column. And the Y are the values for each student's inclination by percentage. Okay, these are the marks or the points. And so this is your Y, and this is measured in percentage. But we know, just for understanding here, it says, find the linear regression for a student's attitude. So Y is the student attitude. For a given score of X. So X is the score that the student earned. Okay. So here we're saying the score is independent and the student's attitude depends on the score. That's what this would mean, right? So now I would like you to enter this data. Again, go back and clear your list, clear L1 and L2. And I'd like you to enter your X column in L1 and your Y column in L2. Right? So once you have done your L1 and L2, now you have to go to Start button again, right? That's where you entered, right? Under Edit. Now go across from Edit, go to Calc, okay? Don't go to Tests. It's Tests, if you recall, those were your Z-test, T-test, one population, two population, and all that, right? So stay on Calc. So go from Edit across to Calc and go down to number 4. It says Lin Reg, AX plus B, right? Lin Reg, and hit Enter, okay? And let's see. When you hit the Lin Reg, you get Y. It first says Y equals AX plus B, right? You see that statement there. And then it says A equals 3.17924523, and B is given to be 30.10377358. Okay, you might even see other ones like R squared and R. If you see them, ignore them for the moment. We will need them shortly. If you don't see them, that's fine. I will also kind of explain how you can make them visible. But these are the ones we need for now. Now, the equation is given to be Y equals AX plus B, and they gave A and the B separately. But it's because A and B are really long numbers. They wanted to keep them separately. So our job is to put all these together and write it as Y equals 3.17924523 X plus B is 30.10377358. Sometimes they like to put the constant first and then the X term, and they would even round it for you. So do not be confused with all of that. Just see what format it is in. So they could round it like 30.104 plus 3.179X. They could do that. And this is the equation of this is your linear regression equation. That's the lin-reg. This is your linear regression. So the calculator makes it so easy for us. The actual calculation, the formulas are really, really tedious. So we used a couple of examples to come up with a way to use calculator to find the A and the B, which in this case, A is your slope, right? And your B is your y-intercept. Together, we put them together to form the linear regression equation. We got the equation to be y equals 30.104 plus 3.179x. Now let's talk about correlation coefficient. Now correlation, we know, is how related two variables are. Okay, so you use a scatter plot to see the display of their relationship. Okay, and if it is reasonably looking like a line, the points are lining up as a close fit to a straight line, then you're able to say, okay, we can even come up with the equation of that line. Now, correlation coefficient, okay, this is represented by the letter lowercase r. And this was developed by Carl Pearson in the early 1900s. So it is an indicator, okay. R measures, R is the correlation coefficient, okay. So it measures the strength and direction of the linear relationship between the independent variable x and the dependent variable y. Think about this. It measures the strength, how strong it is, and the direction, left or right, okay? So to think of it. When we say strength in math, particularly, right, the meaning for strength here would be, is it positive or negative, okay? We talk about, did I switch it around? I'm sorry. Okay, so, well, you can use it interchangeably too, I think. Okay, I should have used the positive, negative for the direction. Okay, the left or right, right? Okay, so it's positive or negative, right? And in terms of strength, we can say, is it again positive or negatively correlated, but is it closer to 1? I'll just explain that to you shortly. So we have various kinds of scatter plots that you can expect. Okay? Some scatter plots may not look like a line, they just look scattered anywhere, okay, all around. And some scatter plots will look really nice, like one of the examples we did. So we have R is a value, right? It's a measurement. So R is a value that lies between -1 and 1. Okay. So if I were to write it as an inequality, I can say R is between -1 and 1. So R can be exactly -1, can be exactly 1, and in between. So if your values lie very close to -1, it tells you how strong the relationship, okay? Or if it lies to +1, the positive and the negative gives you the sign, so the direction. So the direction is, if it is negative, the direction is that it's negative correlation. If your correlation is close to 1, either the positive one or the negative one, you know that the strength is high, right? It's a stronger relationship. So what I want to do is show that if your R is very close to 1, negative 1, we got a perfect negative correlation. It's a very rare occurrence in reality, but if you get it exactly equal to negative 1, that means all the points line up as to form a line. And when we say negative correlation, because of the negative sign, think of the slope. Negative slope means decreasing line, right? So your line will be, the scatter plots will be lined up as a decreasing line. And if it is equal to 1, we call it perfect positive correlation. And the points will line up perfectly to form an increasing line. Okay, so perfect negative correlation is negative 1 with a decreasing line, and perfect positive correlation would be a positive 1 with an increasing line. What happens when R is 0? Because it can't take that value 0, right? 0 means there's absolutely no linear relationship between X and Y. Okay, that's really strong there too. If R is equal to 0, if it's 0, right, absolutely, we're so certain. Absolutely no linear correlation. So if R is, say, 0.2 or 0.5, you know that it is not very strong, but it's strong enough. In fact, to know if it's really strong or significantly strong, we will conduct statistical hypothesis testing on this as well. Okay, we won't be going into details of that in this course, but in advanced stats, you can go ahead and perform the statistical testing of hypothesis. But it's not too complicated. It's very similar to what we did previously with normal distribution. But this also has its own areas of rejection, and therefore that will help us to determine if there was a significant correlation coefficient or not, if the R value is significant or not. Because right now it's subjective, right? If it's close to 1, we say close to 1. What is close to 1? Is 0.5 close to 1? Is 0.8 close to 1? Or is it 0.99 that's close to 1? What do I mean by close to 1? So in order to know that, we have to go to statistical hypothesis testing, because that's where the significance is established. Okay. So look at the first graph, okay? Now the yellow points are your data points, right? You plot them from your table, X column and the Y column, you plot them. You obviously do not see them all lining up perfectly, but they are very, very close, right? To lining up, because you can definitely see that. And there are a few points that do stray off. That's fine. And in the second picture, you notice that there's more vagueness here, because now your points are all scattered a lot more. But then they're also hovering close to the line once you draw the line of best fit. Okay, but you do see that in one case you do have one of the points that's really far off, and here most of the points are clustered close to it. So you can get graphs that are that show these two kinds of scatter plot as well. So if you consider the direction of, let's just focus on the left graph, okay? If you consider the direction of this, the direction is positive because you see an increasing line, right? So we can say that the direction is positive. And what do you know about the strength? The strength is it gets really strong as it gets closer to positive 1 or negative 1. Here we establish the direction is positive. So for it to be strong, it has to be close to positive 1. So are these points lining up? We don't know the R value yet. There is a way to calculate it. But just upon inspection, these lines are so close to the blue line that you can see that it is close to positive 1, right? So it is very strong. On the other hand, you come to the second picture here to the right side. What is the direction here? The direction once again is positive, right? Because the line is increasing. And here too, we want the strength to be considered as if it's closer to +1. Can't be -1, right? Because of this, the direction is positive. But here you can see that the strength is less close to -1. And how do I know that? That's because I see more points are further away from the blue line as opposed to the left graph where all the points were very close to the blue line. Some of them were coinciding with it. But here you have some of them coinciding with it, but most of the points that do not lie on the blue line are farther away from the mark. Therefore, we know that the correlation coefficient is going to be less than the perfect. It's a +1. Put a plus. Less than the +1, which is the perfect positive correlation. So the strength could be super strong in the left diagram, but it's less strong in the right diagram. So here's a picture of 3 conditions possibilities, right? So you have the left picture. This is a positive correlation. To give the definition in terms of mathematical language, we say as x increases, y also increases. And think about this, right? If that is your x value, that will be your corresponding y value. Now, if your x value increases and you're looking at a higher x value, you're looking at a correspondingly higher y value, right? So as x increases, your y values also increase because here your y values increase all the way up to infinity. The x values increase on the right all the way up to infinity. So that is good there. And then here, for the negative correlation, as x increases, y decreases. That is what makes it negative correlation. So let's start here, okay? So there's an early x value. Its corresponding y value is right here. That's a high y value. As my x increases, right, I've moved further towards the right. As my x increases, my corresponding y value has decreased. It's come down, right? So if I look at this x value, that is an even lower y value. So as x increases, your y value decreases, right? Now, if you look at zero correlation, what happens here? It doesn't matter. As x increases, the y also remains the same, right? As x increases, y remains constant. You can see that, okay? This is the x value. The corresponding y value is the same, is there. If you go to another x value on the right, an increased value, it's still the same y. If you go to the end here, it's still the same y. So the y remains constant. So a zero correlation happens when you have a horizontal line. And you can also see a correspondence with the slope, right? Then slope is 0. Slope is always 0 for horizontal lines. So here we are using the same idea and extending it to correlation, and we say that there is no correlation because your R is 0. Okay. So if it is a positive correlation, there's a positive correlation, R is, let me just put it this way, R is between 0 and 1, right? If there's a negative correlation, your R value will be between -1 and 0. And if it's zero correlation, as the name says, your R is exactly equal to 0. Now, also remember, we caution you that a strong correlation does not mean that one affects the other or one causes the other, okay? So remember that strong correlation does not have to indicate what caused. So correlation does not imply causation. What do I mean by that? Now, because you got a very strong correlation, let's say it was very close to 1, it does not mean that x caused y. Okay. So now let's say x and y. X was the number of hours of sunlight. Not the sunlight. Let's use the other example. What was the other one? I think we looked at the length of the bridge and the cost. Okay, so the length of the bridge would be on the x-axis and the cost would be on the y-axis. So because the correlation is quite high, does not mean that the length of the bridge, okay, has affected the cost, or the cost depends on the length of the bridge. That does not have to be. Could be the other way around as well, right? Because what if you had to paint more of the bridge, right? The length was more. Then just like wholesale, right? The costs can actually differ. You can have a better deal because of that too. So we don't know what caused the other. Could be reverse causation too. So we really don't know about that. Therefore, you will never conclude saying that because the correlation was strong, one affected the other. You can't say that. And that's why we say correlation does not imply causation. We talk so much about this correlation and the correlation coefficient and the strength and the direction. But how do I measure, calculate R? This is how we measure it. Beautiful, isn't it? Okay, it looks super complicated, and N here stands for the number of data points. Now, you know X is the X column, Y is the Y column, and you know summation means to add them. So if you look at this as XY, so you need to multiply the X column and the Y column. That will be the XY column. And if you added that, summation would be to add that column. That gives you this first term. You have to add the summation X, which is X column. Add the X column separately, add the Y column separately, and then multiply them. Okay, I want you to really understand here that here you first multiply X and Y and then add them. Here you add the X first and then add the Y first, multiply those two. Okay, that's your numerator. In the denominator, summation X squared means you have to take the X column and square it first. So each X will have to be squared, and you need to take the sum of all those squared X's. That is this. Summation X with the parentheses around it and a square means you'll have to first take the sum of all the X's. We already did that for the numerator, right? So take the summation of the X, the sum of all your X's, and square that answer. Do the same thing for the Y. So as you can see, it can be very time consuming. That is the reason why we really love to use our calculator to give us the output on this. Okay. So we'll come to the calculator part though very shortly. I want to kind of show you how correlation coefficient can be discussed in terms of their strength. So look at this screenshot here. I have 4 of these graphs. Now, which one would you think has a correlation coefficient with a value closest to positive 1, meaning very strong positive correlation? So for positive correlation, you are going to go for lines that are increasing, right? So because of that condition, you are going to actually ignore this and this. Why? Because they both show negative correlation, right? The question was, which one is a positive correlation? So for the positive part, you look at the line and see if it's increasing. So we got these two. Now we need to narrow it down. We eliminated. We need to now choose between the two. Now, remember, it's linear. So you want your points to line up as close to the line as possible. And here you see that it's first of all not a linear formation. It's some other formation. It's not linear. If it's not linear, we call it non-linear. So this one is not linear. But this one, the points are going up and down the line, but they're hovering very close to the line, right? So this is also eliminated. And this is your correlation with the positive correlation with the value closest to +1. Oh. So we're going to do an example to calculate R, which is the correlation coefficient. And in order to do that, you want to make sure that your calculator has the setting right. So now go to, this is TI-84 plus, right? So I'm going to write that down here. So I want you to do second and then 0 so that you get catalog. The catalog, the word catalog you see is typed in, is written in blue. That's just above the 0 button. So second and 0 button will take you to the catalog. Okay. So there, scroll down all the way to diagnostic. I think it's in alphabetical order. Yeah, so you start with the absolute value and angle and so on. So go all the way down to D. I don't think there's a way to search for D. I don't know about that, but go for diagnostic off and on, and you want to choose the on. Diagnostic on. So click on that, and then it'll take you to another screen. Hit again, and it will say diagnostic on done. Okay. So if you do it twice, it will say done. That means you have turned it on. This would allow you to begin to see other features, like you will see the R and all that in your calculations when you do linear regression calculations. Okay. Now that's what I meant when in one of our previous examples, that you might be able to see the R or you may not. So this diagnostic on would make sure that it makes your R visible. Okay. So let's take a look at an example and see if we get the same values. All right. This example gives you a table here, and I'd like you to perhaps pause the video and enter these in your L1 and L2. Make sure you clear your screen, clear your lists. So to clear your list, you go to Stat, Edit, number 4, Clear List. Go down to Clear List, and then I want you to clear your L1, L2, whichever one. So each time, for each list you want to clear, you'll have to go through this process. So clear list L1, hit enter. And then go again to edit, clear list L2, hit enter, and so on. Okay. Once you're done clearing, make sure you enter these values, for which you have to go again to Start, Edit, and Edit. First one. All right. Once you have done all these things, you will go back to Stat. It's all happening in Stat. Okay. From Edit, you go across to Calc and go down to number 4, which is LinReg. Okay. When you hit enter at LinReg, go to number 4 and hit enter. And there it says Xlist. Okay. So because I'm asking you to enter this in L1 and this in L2, right? So I'm going to ask you to put the Xlist as L1 and the Ylist as L2. You have to enter those two. It says frequency list. Skip that. Store reg equation. Skip that and hit calculate. Okay. So I'll just write that too here. Hit calculate and you get a list of details. Okay, so you will see y equals ax plus b. This is what we did in one of the previous examples, right? You see a as 4.16666, etc. 7. B is negative 135.2. And you have now r squared and r. This is appearing, if it didn't appear to you before, and if it does now, it's because you turned on the diagnostic. Okay, so r squared comes out as 0.99980800369, and r comes out to be 0.999900128. Okay, and your focus should be on the r, not the r squared. You're going to use the r. This r is your correlation coefficient. So the calculator gives it to you right away. You don't have to, it does that complicated calculation in the background though, but it gives you r. And this r, as you can see, is 0.99. It's so close to 1, so you can tell that there is a strong positive correlation between the height and the weight. Okay. Or in other words, as the person's height increases, the weight increases, right? And we can predict that the weight would increase. So I want to write that out here. Okay. Since R is 0.99, which is very close to positive 1. This implies very strong positive correlation, right? It's nearly perfect. If you have a strong positive correlation, it implies that as x increases, the y increases, right? That means as the height increases, the weight also increases. We can predict that the weight also will increase. Okay, and that's an important use there, isn't it? So I'll give you another set, and we'll calculate the correlation coefficient for that, and then interpret the result. Okay. Here is your next problem. Height is in inches, and then the IQ scores are given to us. Okay. So please enter height in L1 and IQ in L2. Make sure you clear the lists and then enter them. That's a good time to pause the video, enter them, and then track along. Okay, suppose you did all the calculations, and let's see if our answers match. So when I did the STAT calc number 4 LinReg, linear regression, this is what I get. AX, we're asked to only find the correlation coefficient. So I'm going to skip all the A, the B, and the R squared. We don't need all of those. And then I come down to R. Okay, R is 0.00912414484. This is what my R is. Okay, so now they want us to interpret this. Okay, now is this positive? Yes, you know that it's positive because R is a positive number. It didn't give us a negative number, so you know the direction is positive. Is it strong or weak, right? That's the strength. Is it strong or weak? So if it's strong, it must be very close to positive 1. In this case, it has to be positive 1, right? Because the R is 1. But you can see that it's 0.009. It's actually closer to 0 rather than 1. So it is a weak positive correlation. Okay. R equals 0.009 indicates a weak positive correlation. So you're talking about the strength and the direction. So that's really important. Correlation between height and IQ. So you can kind of say there's not much of a link between a person's height and IQ score. Right? So that is what this kind of indicates to us. So we are not saying that the height depends on the IQ depends on height. We're not saying any of those things. We're just saying that the link is really weak. The connection, the correlation. Correlation is the correlation, right? So the relationship is kind of weak. The link between these two variables is weak. Now let's talk about line of best fit. The purpose of getting the equation is to help us to make predictions. Okay, so the purpose is to make predictions about the data set. For missing values. And we have two types of prediction. One is called the interpolation. And this is a process of predicting inside the observed X values. Inside or within. And here the results would be reasonable and reliable predictions. And we have extrapolation that can happen. Here, this will be the process of predicting outside the observed X values. And you can have two types of problems that come from this. You could have results because you're going outside the X value, the observed values. The results could be less reliable but reasonable. No. Sometimes it can be completely useless, as in results could be both unreliable and unreasonable. So when we make predictions, we have to be careful about the circumstance, the values we're choosing, and what kind of prediction we're making. Is it interpolation or extrapolation? And if there is value to what we're doing. Take a look at this data set. A random sample of 11 statistics students produced the following data, where X is the third exam score, and this is out of 80 points, the score. And Y is the final exam score, that's out of 200 points. So first, you can quickly recall, this is out of 80, and this is out of 200. And you can see the values that way. Now go ahead and, again, clear your lists and call this L1 and L2. They already gave us as X and Y, so we'll keep it the way it is, L1 and L2. So if it is X and Y, you know that X goes on the horizontal axis and Y goes on the vertical axis. Okay, once you have entered the data, then you could go ahead and do the scatter plot, okay? And you have to recall how we did the scatter plot. So remember second stat plot, which is Y equals button, and then plot 1, then go to type, first keep the plot on, then go to type, then Xlist will be L1, Ylist will be L2, and then the mark will be a square. Yeah? And then when you go to the graph, you will see the points, the scatter plot. Yeah. Once you have those points, that's just your scatter plot. But if you wanted to draw the line of best fit, okay, what you can do then is go to Y equals, go to Y equals, and in Y equals, hit vars, okay, Y equals and hit vars. And that vars opens to a list down, Windows, Zoom, GDB, and so on, right? So go to number 5, which is statistics. Yeah. Go to number 5, which is statistics. And then go across to the EQ. Let me see if I can write this information here by the side. So Y equals. And from there you hit vars. And in vars, you went down to statistics. That was number 5. And from statistics, it took you to this XY, sigma, EQ, right? Those things. So go scroll over, use the right button to go over to EQ, and then go down to the first one, which says Reg EQ, regression equation. Okay. It will insert that equation in your Y equals. Okay, so you can type the equation if you want, but this will help you to insert the equation, and then it will draw that line on your scatter plot. Okay, so see if you can get this. Now, if you have difficulties with this for some reason, always use Excel spreadsheet. Excel is free, so you can use Excel to graph and get the same information. Okay. And when you do that, your graph would look like this. Remember, your x-axis has the third exam score, and your final exam score should be on the y-axis. This is, the x-axis is always independent, the y-axis is always dependent. All right? You can go back and also find your regression equation if you wanted, because we're going to do that actually now. So if you wanted to type in the equation, you could do that too. Okay. Let's go to the regression equation for which we want to stat, calc, so near that here. Stat, calc, and you go down to Lindred, and that will give you, right, all of them, y equals all that. So let's write that the way we see it. And make sure that you are calling upon the right list. Of course, under Lindreg, you'll have Xlist, Ylist, and then those are the only things you'll have to do. Go down to calculate and hit enter, and you will get y equals ax plus b, with a as 4.827394209, b is negative 173.513363, r squared is 0.439692104, and r comes out to be 0.6630933591. All right. So right now we are focused on this regression equation, this blue equation. And so the equation for that, I'll just write it down here. Y equals ax plus b, right? So round it to 2 decimal places. So a, when rounded to 2 decimal places, would be 4.83x plus b. So b was a negative, so I have to remove the plus and make it a minus, 173.51. Yeah. So this is our line of best fit. This is the equation of the line of best fit. This is our linear regression. Now we're going to use this to make predictions, okay? And for that, we're going to make it completely mathematical. I want you to quickly observe the x values. The x, in your x column, your values are between 65 to, the minimum is 65, right? The maximum is 75, okay? So that's good. Now we always predict the y values, right? So we have to look for the x values and choose an x value to predict the y value. If there are any missing values, for instance, do we have 68? We don't have a 68 here, so we can predict for 68, isn't it? Like that, you can look for numbers that are not here, because if the numbers are already here, there is a predicted value on the other side. So that is one of the big uses of linear regression, is to be able to predict the values. So let's come here, and I want to write the equation again. Y equals, in fact, this is a regression equation which is predicted, right? This is predicted line. So therefore we put the y hat to indicate that we got the line of best fit. It is the same thing as y equals mx plus b, but remember, the notation is what tells us what we did, how we got this. We got this as the line of best fit, where most of the points pass through it, and the points that do not pass through this line are hovering very close to that line. So we have two kinds, right? We just saw interpolation and extrapolation. So I want to start with interpolation. And interpolation says it's a process where you predict inside the observed x values. So the x values, we saw that they ranged from 65 to 75. 5. So you have to stay within these x values, and for anything that's missing within these x values, that is what we will interpolate. Okay, interpolation is reliable and reasonable. So we like to do that. So let's perhaps get a prediction for when x is 73. Okay. When x is 73, what is the predicted y value? Now, if you think about this, the 73 is within the x values, right? Therefore, it's interpolation. And therefore, it's reliable. It's going to be reliable because you're not going outside this scope. And 73 here is x value, which stands for the third exam score. And you're using this third exam score to predict the final exam. Okay, that's what we're trying to do. So this is at this point a pure mathematical problem. So y hat will be 4.83 times 73, because your x is now 73, minus 173.51. So that gives you 352.59 minus 173.51, which comes out as 179.08. So we predict that the statistics students who earn a grade of 73 on the third exam will earn a grade of 179.08 on the final exam. This is on an average, not exactly, right? So students who get this, we predict that they would earn about this value. Okay, they might get 180, they might get 178, but it's going to be in that neighborhood on an average. Okay, and look at the answer. Is this reasonable? Yes, it's reasonable, first of all, because our x choice was from within the x values, and our y response, this is out of 200, right? So it is both reasonable and reliable. Okay, so the fact that your x was within is reliable, and the answer, the resulting answer, was a value that was within 200, which makes it reasonable. It's reasonable to expect them to earn 200 points because 73 is out of 80 points, right? So it's reasonable to expect that. So this is good, a good prediction. What about extrapolation? Extrapolation is when you will choose values outside the x values, right? Let's write that out here. Once again, the x values are still between 65 to 75. But when we choose an x value that is different, let's say when x is 77, okay? We didn't go too much outside the scope, but we did go outside. So at that point, we have made it less reliable. What is the predicted y value? So this time we look at this and say, okay, this is not in x value range. Immediately that means it is less reliable. And if you go back to how we define this, extrapolation is the process of predicting outside the observed x value. So in that sense, we did choose something outside, but there are two possibilities. It could be less reliable but reasonable, or it could be unreliable and unreasonable. So we got the less reliable, okay, and see if our corresponding y values are coming out to be reasonable. So let's go ahead and plug this in. .83 times 77 minus 173.51. And that calculation comes out to be 371.91. Hey, look at this answer. This answer is out of 200, right? It does look reasonable. I mean, it looks really, the student must be really, really good because it's 198 points. So it must be really close to 200. But on an average, students can get this score. It's not impossible or unreasonable. Therefore, here is a result that is less reliable because the value of 77 was outside the X values, but it gave us a reasonable prediction because this is a number, a value that can happen. It's a score that can happen. So we got less reliable but reasonable answer. Okay. And in extrapolation, we also have another option. Okay. So what if I chose X to be 90? What is the predicted? Okay, you can see right away, clearly through, that X equals 90 is outside 65 to 75 range, 1. And secondly, it is more than the highest score, right? More than 80 points. You can only earn 80 points, but here you are choosing more than 80 points. Okay, let's say some crazy calculation. I've seen some places where extra credits are docked on these scores so that it's more than 80, so they get more than 100%, which is mathematically jarring. But say X was 90. Can you predict Y? So let's see what happens when you predict Y. So Y hat will be 4.83. Okay. Times 90 or minus 173.51. Hundred was 434.7 minus 173.51, and the answer is 261.19. So you got, first of all, you started with something that's unreliable. Okay, let me write that there. Unreliable. And then you got an outcome, an output that was unreasonable, because this has to be out of 200 points. And you're getting 261.19 points. That's the prediction. So when you go too far outside your X range in extrapolation, you clearly see that your results are both unreliable and unreasonable predictions. So we always recommend that you stay within bounds and work on interpolation, work within the observed X values. Let's take a look at this example here. In 2012, the CDC published data on the average weight of American female children by year. Using ages 1 to 7 of this data, researchers made a linear regression with age in years as the X variable and weight in pounds as the Y variable. The equation of the line of best fit is given to be, in fact, I have to put a hat here. So Y hat is 5.78x plus 17.56. According to the line of best fit, what would you predict the weight to be for a 10-year-old female? So I'm going to write the equation again. Y hat equals 5.78x plus 17.56. Okay, and let's quickly make a note of what they stand for. Here. X is the age in years, and Y hat is the weight in pounds. That way, when we are ready to interpret the answer, we'll have what they stand for. Okay, now they've said, predict the weight for a 10-year-old female. So the age is given to us and we're asked to find the weight. So go ahead and plug that in. Times 10 plus 17.56. $75.36. What we've done is interpolation or extrapolation. Clearly, we've gone outside the range because if you see, this is for data that's from 1 to 7 years, right? And we're asking for a 10-year-old. So we've gone outside, so we will have to content with less reliable but reasonable, or less reliable and unreasonable? Now, is it reasonable for a 10-year-old child to weigh 75 pounds? Okay, that's reasonable. So we say the predicted weight of a 10-year-old female is 75.36 pounds. Yeah. We'll look at another example. How does shoe size vary with height? The height and shoe size of 40 males were measured and recorded. Using this data, researchers made a linear regression with shoe size as the x variable and average height in inches as the y variable. The equation of the line of best fit is given to be y hat equals 1.89x plus 51.68. What is the average height of a male with a shoe size of 11? Okay, now this is actually an interesting one because this is a real application where one of the detectives used this method to identify possible suspects and criminals. So what they did was in the crime scene, when they saw the footprint, the shoe print, I mean, not the footprint, but shoe print, they took the size of the shoe print and figured out the shoe size and used the shoe size to predict a person's height. And that's how they kind of were able to narrow down on suspects, and they were successful with that. So it's really interesting to see that there is correlation between shoe size and height. And here we have a linear regression that gives a connection between the two. So let me write the question again. Y hat is 1.89x plus 51.68. And as always, we need to identify what y stands for and x stands for. X is given to be the shoe size. And the average height in inches is the y variable. But that'll do. Now, what's given to us is the shoe size of 11, and they want us to find the average height of a male. So you're predicting y by plugging in for the given shoe size, which is 11, for x. Then see if this is reasonable. Well, you're asked to interpret this. Now we do not have here it says the height and the shoe size of 40 males were measured and recorded. So if that was the case, we don't have access to that list. So we really can't tell if this is interpolation or extrapolation. So at this point, we cannot make any judgments. We will just interpret the answer. We'll just say the average height of a male with a shoe size of 11 is 72.47 inches. So with that, we come to the end of chapter 12. I hope you enjoyed this chapter, and I will see you in the next and the final chapter, chapter 13. See you then.